This page here, page 25.
This is the 4.2 packet. I think I looked though. I have these two. Okay, thanks.
Okay, so page 25. Number 1 says use sigma notation to write the sum. Okay, so we want to be able to get this into sigma notation. Typically, we want to create a pattern where if I plug I equals 1 into the first, into the expression, into the rule, it'll give me this value. If I plug 2 into the same expression, I'll get this value. I equals 3, and then dot 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 means that there's going to be a gap, and then I equals the upper bound. We have to figure out what is the upper bound that will allow us to get that final value. Sorry, let me get this to show up. Okay, so let's create our summation notation here. Okay, so with each term, I'm just going to I'm going to put down the easy stuff first, which is what are the parts that are not changing? Because the parts that are not changing are just going to stay as constants. So which parts do you see that are unchanging? 7. And then the plus sign. Okay, so then we know that the 3, the 6, the 9 all has to involve I somehow, right? Has to create that pattern. And the 4, 8, 12 is also involving I as well. So what pattern can I plug I into that will allow me to get a 3? If I plug 2 in, I get a 6. If I plug 3 in, I get a 9. 3i, let's test it out. Okay, so 3 times 1 is 3, that works. 3 times 2 is 6, that works. 3 times 3 is 9, that works. So what's going to be that final I value that will give me 18? 6. Okay, good so far. So now we got to figure out 4, 8, 12, all the way to 24, what can we put here that will allow this pattern to show up? Any idea? Say it again. 4i. Let's try that. Okay, so 4 times 1 gives us 4. 4 times 2 gives us 8. 4 times 3 gives us 12. All the way up to 6. 6 times 4 is 24. Right. So whatever your guess is, it's always good to, write it down, but then test it out. Make sure that it will actually produce each of the terms that you want it to produce. Okay. All right, let's do a limit definition problem. Right. So, are you okay with number 1? Okay, so this is Jake. This is page 25 in the 4.2 packet. Yeah.
For I, is it always going to be like 1, 2, 3?
Yeah, it'll be 1, 2, 3. Yeah. Okay, limit definition. So here's limit definition. I'll write this out. You got the width component, and you got the height component, which is inside F. Okay, first things first, we have to just go ahead and replace all the A and B values that we see. We know the width is going to be, we know that -1 is the A value, 2 is the B value. So 2 minus a -1 over n would be 3 over n. Okay, I'll rewrite. There's my width component. Again, we're not going to replace n with a number, because if we do, then all of a sudden we're down to approximations again, right? We want exact values. So we're holding on to n because we're pushing the number of rectangles out to infinity. A is -1. Okay, any questions so far? Okay, we know that this is in function notation. These are not compatible, right? We can't multiply 3 over n times f of -1 plus 3 over n, because these are not, we got to get this out of function notation. So we have a function that is, which is gathering all the y values for our height, right? So this is the specific function that's telling us every point what the height is at every moment in time. Okay. So I know saying h of x, I'm going to just bring it back in terms of f. So let's say that f of x is 3x minus x squared. Okay. We have to somehow involve this argument inside the function. So a way to make sure that the argument, that you're putting the argument in all the right places, go ahead and do this extra step. Rewrite the function, but then literally leave an open space wherever you see an x. Okay, that way you're basically, you're reserving where your argument is going to go. Okay, all right, everybody okay from the function to the setup? So now all the open spaces will be the argument that will be involved. Okay. Yeah, I'm going to leave that space open so to show the transition I'm about to make. Okay, are we good so far? Okay, so now we have a perfect substitution because this f of -1 plus 3 over ni is going to be replaced with this whole expression. Right? This is now the full height component that is now compatible with this 3 over n. Okay, questions so far? Okay, so we've gotten everything out of function notation. Now it's just a matter of algebraically cleaning up. Okay, we still have quite a few things to do here, but now it's just all algebra for now. Okay, so we're going to FOIL this out, distribute this through, combine like terms, get all this cleaned up, and then we have to also multiply everything through by 3 over n. Okay, but first things first, I'm going to get this FOILed out first. Okay, I'm going to wait to distribute the negative through. I'm just trying to get this binomial square to be a little bit more cleaned up. Okay, distribute the negative through, distribute the 3 through. All this time, just have to remember that, okay, we still have to worry about this width down the line, okay. Combine like terms. Okay, so things are cleaning up here. Any questions so far? Okay. So all this is the cleaned up version of the height component. We still want to multiply that width component through, right? So distribute the 3 over n through. Okay, any questions here? Okay, let's bleed into number 4 here. This trapezoid approximation, we can do this later. Let's just use this space if we need to, if we need the space. Okay, so now every term we have to involve summation formula, okay, to resolve this summation notation there. So every term I'm going to put a summation next to it, but then along the way I'm also going to push the coefficients out in front, because one of them will be summation 1, one of them will be summation I, and the other one will be summation I squared. Okay, and all this is on the front page of the packet. Okay, how are we doing so far? Good. So, okay, so from here, we should be able to isolate exactly what needs to be replaced, right? We have a perfect replacement for that summation 1. We got a replacement for summation I. We got a replacement for summation I squared. Summation 1 gets replaced with n. Summation I gets replaced with n plus 1 over 2. And then summation I squared is n plus 1, 2n plus 1, all over 6. Okay, every fraction, we should get matching degrees between top and bottom. So here I got negative 12n over n. Right. For limit as n approaches infinity, we just compare degrees and pull the leading coefficients. Second term here, if I distribute the 45 through, okay, but we're only concerned about the ratio of leading coefficients. Degrees are the same. Okay, we'll come back to that. And the last one, it looks like there's a lot of terms to expand, and it is, but we really are only targeting the highest degree within the fraction, right? So to get there, just have to multiply the 27, the n, and the 2n. There are more terms than that, but we know that with limits as n approaches infinity, once we get past the highest degree, the rest of it is just going to fall away. So 27 times 2, 54, n to the third. Okay, we know there are more terms, but they're all going to be a lower degree. They're just going to wash out. Okay, so the strategy for evaluating limit as n approaches infinity, we don't plug any values in, we just compare degrees. Okay, if the degrees match, we just pull the leading coefficients. So here, n to the first power, these are both matching degrees of 1. We take the ratio of the coefficients, negative 12 over 1. So we know that the limit as n approaches infinity of this expression will just lead us to negative 12 over 1. Okay, so that cleans up nicely to just be a fractional value. Second, limit as n approaches infinity. The highest degree is 2, so that will just produce 45 over 2. Lower degree doesn't matter. Okay, bunch of terms after n to the third, but we already targeted and found the highest degree. So negative 21 plus 22.5 gives us 1.5 or 3/2. So this number is significant in the sense that this is telling us the exact area under the curve for this particular graph. We're no longer in the approximation region. Now we're finding the exact area. Okay, questions? Okay, it's a lot going on, but I want to see if is there any parts that you want me to clarify or go over again?
It's really long.
It's really long, yeah.
It's a lot to get.
Mm-hmm. Yeah, but I'll be looking at your work, and if I see a minor mistake, I'm still going to give you the majority of credit because I see how your work is flowing through. Okay. All right, so the summation formulas will be given to you. The area formula will be given to you. Okay, just have to know how to use them. All right. Okay, number 3. Now we're dealing with approximation here. This is use 3 right-handed rectangles to approximate the area of this region. Okay, so here we have to really build the width from scratch. So we have to go through this formula: width equals b minus a over n. Okay. Find the a value, the b value, and the n value. A is 2, b is 4, what's n? Yeah, we have 3 subintervals. Okay. B minus a over n, 4 minus 2 over 3. Two-thirds. So you know that the width of every rectangle is 2/3. We just now have to build our subintervals from the left endpoint. Okay. We know we're starting at 2. And we're going to keep adding 2/3 until we reach 4. Okay, so 2 plus 2/3, that's 4. 6 over 3 plus 2 over 3. 8/3, right? Yeah, got to find common denominator, right? Because if you think of 2 as 4 over 2, you can see that adding 2 fractions together. Okay, plus 2/3 again. 10/3. Plus 2/3 again. Yeah, 12/3, which is 4. So that does confirm that we are able to create 3 subintervals, all the same width from starting point to ending point. Okay. It's asking for right-handed rectangles, so I think we have everything that we need. Every subinterval has a right endpoint. Okay, so we don't have to worry about what the graph looks like, but I just kind of show you, if the graph was 1 plus 3x squared, it may look something like this, right? And in every rectangle, we're just going to be attaching to the right endpoint to the graph and creating this right-handed rectangle. Okay. Okay, so now we want to pull the width and height for every rectangle, right? Every rectangle area formula is width times height. Okay, width of every rectangle is what? 2/3. So it'll be 2/3 times the height. The height, we want to attach the x value to the graph. We want to say 2 times 8/3, right? It's f of 8/3, because 8/3 into the function is going to give us a decimal value. But right now we can just represent using function notation. Huh?
So when do we find the points? Like
Good. Right. So we find the points in between if it's asking for midpoint rectangles. Right. Then we have to spend the additional effort to find the midpoint within each subinterval. But if it's left or right, you can stop once you get to your subinterval, and because you know that both your left and right are found. Okay. Next up, width of 2/3, height of f of 2/3, f of 10/3. And then finally, width times height, f of 4. Okay, we spend our time entering these into the calculator, plug 8/3 in for x, 1 plus 3 times 8/3 squared. That'll get a decimal value, times 2/3, that'll give us the area, and then we just spend the time plugging into our calculator. I just factored the 2/3 out, so I don't have to enter as many numbers. Okay, are we good with rectangle approximation? No questions? Okay, all right. You guys may be out of room for the trapezoid approximation, but if you can find space, it's not going to take a lot of space, I don't think, to do this one. Okay, two trapezoids from 3 to 20. Here's the trapezoid area formula. It's width over 2, height 1 plus height 2. Okay, each trapezoid, you're only going to pick 2 heights for each trapezoid. We're not going to add up all those heights, okay? Even though there's all these numbers in between. Okay, so this is 2 trapezoids, so you want to span your intervals so that every interval is, they're overlapping, but then at the same time, each interval covers the same number of order pairs. So you play around with the numbers there, make sure that you create subintervals that are equal in the sense that they are spanning the same number of order pairs. So you should have one interval from 3 to 11 and second interval from 11 to 20. That's got that? Okay, so now subtract your x values to get the width. 11 minus 3 is 8. 20 minus 11 is 9. So you have the width component for each trapezoid, and now you're just going to gather the heights. The heights is just going to be where those brackets start and end. You're only going to use these values here. Okay, so you have to do 2 trapezoid areas, okay, separately. Width over 2, height 1 plus height 2. Okay, width over 2, height 1 plus height 2. 4 times 13, 4.5 times 26. Okay, you guys okay? All right, let's do some power rule problems. Okay, I'll just create some problems, and you guys can just put this on a separate sheet for us to do. All right, so before we do power rule, we have to go through our cleanup stage, right? So radicals convert to rational exponents. Any variable that is sitting in the denominator, we got to push it up to the top. So let's just spend the time to clean up each of these terms. And once every term is cleaned up, then we can just do power rule all at once for all of them. Okay, how do you handle this 7th root of x?
Put it on top.
Okay, what would that look like?
3x.
Okay, good. So the rational exponent form of this is x to the 1/7. And then we can push that to the top to be x to the negative 1/7, okay? Second term, same idea, push that to the top. The e squared is already cleaned up, so we'll leave that alone. Okay, every term is set up and ready for power rule. We're going to add 1 to the exponents for each of these. So common denominator here, I'm going to add 7/7 to get that +1 to work out. Okay, good so far? Now, what about that e squared?
Just like a constant.
That's just a constant. E squared x, yeah. It's not, you know, it may be kind of misleading here. You're looking at this going, well, can I make the e cubed over 3, right? But e is not a variable. That's just a constant. That's just a number. A number will just rise up to a degree 1, right? So you can make it e squared x plus what? C. Okay, so that's your answer, but we're going to see if we can do some more cleanup here. Going to reduce the 3 and 6. Good. All right, let's do one more. Okay, let's do one more power rule problem. Okay, 2 square root of x cubed minus 5 root x plus pi all over square root of x. Okay, so here's what we can do. We can take the time to rewrite each of our radicals as rational exponents. We have to resolve that denominator, but there's multiple terms up top, so I think the easiest or the cleanest way to do it is let's just go ahead and split up into 3 fractions, right? Split into 3 fractions that we have 3 independent terms that are not going to conflict with each other, and then within each term we can just try to do cleanup within each to get every term ready for power rule. Okay, how do we rewrite this square root of x cubed? What's the rational exponent for that? Good. All right, so there's a hidden 2 here. Just be careful, right? This is not 1/3. This is not just 3. This is, or not 2/3 either, right? It's 3 over 2. That square root is 2 there. Okay, we'll split every fraction up. Okay, how can I resolve this first fraction here? Okay, bring it up to the top, it becomes x to the negative 1/2, and then we're going to be adding exponents, right? So 3/2 minus 1/2 gives us just what? Okay. Okay, how about a second term? Just 5. Okay, last term, the x is going to come up to the top. So all that work is just to prepare each term for power rule. So we haven't done any calculus yet, right? So that's why we've held on to our integral notations. But after the next step, we can drop those notations and include the plus c, right? Okay, so power rule, every term is power rule ready. 2x becomes, right, 2x squared over 2. What does 5 become? Good, right. Don't make 5 go away to 0. I know that's a tendency. We're used to derivatives so much that we want to make that constant go away. But antiderivative, your degree will rise by 1. So 5 becomes 5x. Okay, pi is a constant. It just stays in front. Add 1 to the exponent. Negative 1/2 plus 1 or plus 2 over 2 is 1/2. Okay, do some more cleanup here. X squared minus 5x. Flip that 1/2 to be 2.
Second to last, why do
You mean down here? The reason why is because we're following the rule for power rule. So power rule says if I have u to the n du, it'll be u to the n plus 1 over n plus 1. So whatever new exponent I come up with at the top, it's going to be copied down below. So these numbers will always match. Okay. All right, tomorrow in class, I'll do more of the problems involving general and specific solution, but hopefully you guys feel more comfortable going through the majority of the types of problems that you're going to see on the quiz.
Questions is the quiz going to be? Like one of each?
Front and it's going to be 8 problems, front and back.
Is there like a list on it where all the topics? Because I know it's for.
Yeah, it's going to be 4.1, 4.2, and 4.6. I have a packet I gave my students, but it's on my website as well. I think I'm out of it though, so I don't have those. But yeah, it's going to be basically everything we did in just now, power rule, and then finding general antiderivative and finding specific antiderivative. Yeah. So those are your topics. All right, thanks guys.
Thank you, I'll see you tomorrow.
Yeah, see you tomorrow. Thanks guys. Bye.